Hey everyone, Morgan here. So we're going to be talking about waves and light today. And this is the Atoms and Light lecture outline for honors chemistry. So a wave is a disturbance traveling through a medium. Now we have a water wave pictured here. And while we're not going to be studying water waves specifically, they do illustrate the type of behavior that we will be talking about. Now, we're going to categorize waves in one of two ways, the first of which is a longitudinal wave. Looks something like this. Now, imagine you have a big slinky laying flat on a tabletop and you just move it side to side. That's what's happening with this. And it's not of a lot of interest to us in chemistry, although it is very valuable in discussions of physics. So we say the displacement of the medium is in the same direction as the propagation of the wave. Okay, now we can pretty much forget about those for now and go on to transverse waves. This is what a transverse wave looks like, and this is what a water wave would be like. Okay, this is a great diagram. You need to spend some serious time studying it. Okay, we're going to talk about all the things in this diagram in a moment. So a transverse wave waves up and down, but travels left to right. Okay? We got a good table here to fill in. The symbol for wavelength is the Greek letter lambda. It is measured in meters, and it's the distance between two consecutive wave crests or troughs. Frequency is the Greek letter nu, measured in hertz, although I typically just write 1/2. And it's the number of waves that pass a given point per unit of time. Period, t, is measured in seconds, the time between two consecutive waves. Amplitude A would be measured in meters, and it's the height of a wave, either up or down. And the wave number is nu with a bar on top of it, measured per centimeter, and it's the number of waves per centimeter. You can pause this if necessary, get this table filled in. Start up again when you're ready. All right, the electromagnetic spectrum is a continuous spectrum that goes from low energy radio waves to high energy gamma rays. Okay, all of that radiation travels at the same speed. The speed of light is given the symbol c. Okay, and you see radio, micro, infrared, visible, ultraviolet, X-rays, and gammas. This is listed in increasing energy, decreasing wavelength, see the waves are getting closer together, and increasing frequency. Now, this is the album cover for Dark Side of the Moon. Amazing album by Pink Floyd. You're noticing that there is a prism here, and that white light is hitting the prism and spreading it out into a rainbow, except that's actually not a real rainbow, and that is not a real continuous spectrum. Okay, it's got several problems with it. It's upside down, the colors are monochromatic, and they don't fade into each other. This is what a real continuous spectrum would look like. First off, the red would be on the bottom, not the top, and the red changes its color as it goes into orange. And there's really not a way that we can just sit there and say, oh, this is where red turns into orange. It just fades from one to the other. The word gradient is good if you're familiar with that word. Now, the visible part of the spectra is low enough energy that's generally not going to hurt us. Some very bright visible light can hurt humans, okay? And you're seeing the low energy red end on the left and the high energy violet on the right. So when somebody says red hot, that is actually mislabeled. That's a misnomer, okay? Red is a cool color. Violet is a hot color. All right, wavelength and frequency are related to each other by the equation C equals lambda times nu. C is 3.00 times 10th meters per second, but I don't really need you to memorize that. It'll be provided for you on any tests or homeworks that you're doing. Remember, the hertz is 1 per second. So when I take meters times 1 over seconds, I get meters per second. Okay. Pause as necessary. So, radio waves, we should talk about them. We're starting a new page here in the outline. Radio waves are low energy, okay, good for short range two-way communication, go a few hundred miles, but you can't send signals, to the moon and back. And because of that, microwave communication was developed by NASA in the late 50s, early 60s. It's good for long-range communication, okay? It's also the basis of modern satellite phones. Remember, you have cell phones that work off of cell towers. You're probably not using a phone that's bouncing off of a satellite. I'm going to go through these kind of quick, but you can pause them whenever necessary. Infrared, used for stuff like night vision goggles. Okay, there are snakes here in California that can actually sense infrared, and they hunt by looking for heat signatures at night. And military kind of got the idea behind that, came up with the idea of these night vision goggles. Now, visible light is what we used to see. Okay. Queen of England, Elizabeth II, pretty much wears the same outfit every day, just in different colors. Okay. Somebody actually spent some time and put this together. Kind of cool. Visible light is how we see. Now, ultraviolet is the first part of the spectrum where it's high enough energy. It can actually do some damage to us. We use it for sterilization, okay, killing bacteria, okay. It's a high enough energy that it is of danger to us, cause skin cancers, but it has a really weird little side effect, and that is it can actually produce vitamin D in the human body. X-rays, we use these for medical imaging, okay? High energy, penetrate the body, okay? Very dangerous. Do not want to be exposed to those unless you have to be. And then gamma rays, which is kind of a blanket term for anything with a wavelength that's shorter than X-rays or an energy higher than X-rays, okay? This will do great damage, and if you're starting to get any ideas, nope, sorry, not going to happen. Okay, you're just going to die if you get exposed to a lot of it. Now, cosmic rays is kind of a misnomer thing. It's really not a part of the electromagnetic spectrum. We're talking about high energy protons and other atomic particles. They're just moving at the speed of light. Okay, they're sourced out in space somewhere. Okay, now, we should remember that wavelength times frequency equals the speed of light. I want to look at some math dealing with that today. So, our journey really starts here with something called the Ultraviolet Catastrophe, which is very misnamed by some drama queen physicists. In the early days of us trying to study the energy of a wave, what we saw was that the equations that predicted the energy were very accurate through radio and microwaves, visible, etc. But by the time you got to ultraviolet, they just didn't work anymore. So they ended up calling that the ultraviolet catastrophe. It's this silly name. But what it tells us is that the classic wave approach to radiation, especially visible light, wasn't working. Okay, and wave mechanics was not giving us correct answers. So we knew that visible light traveled as a wave, but maybe there's more to the story. And that started to develop with a guy named Max Planck, who told us that the energy of electromagnetic radiation is always proportional to a specific number. Now, this is like going in and buying ice cream. You can buy 1 scoop, you can buy 2 scoops, you can buy 3 scoops, but you can't get 1.75 scoops. It doesn't work that way. And it's the same with energy. You can have this amount or that amount or the other amount, but you can't have anything in between it. And this is for the energy of electromagnetic radiation, specifically visible light. Okay? So we say that that energy is quantized. And by saying that, Max Planck was implying that energy comes as packets, or that electromagnetic radiation, when it's absorbed or emitted, is a particle. Not when it travels, but when it's absorbed or emitted. Great stamp that gives the relationship that we now call the first quantum hypothesis, that energy equals h times nu. So frequency and energy. The energy of a photon is related to the frequency of light emitted or absorbed by this equation. E equals h nu. H is Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds. Now, the photoelectric effect was what actually proved to us that Planck was right. We see in here this stamp from Germany in 1979. The light incident upon a very active metal could cause electrons to be ejected from the metal. Works with white light, mixture of all wavelengths. But if we go into monochromatic light, the lower energy end didn't do it, but the higher energy, like the blues and the violets, did. And the higher energy the light, the more energy the electrons left with. And Einstein in 1905, 5 years after Planck's proposal, said that Planck's theory worked to explain this because the light particles were like cue balls if you were playing pool or billiards. And if you hit it very gently and it hit another ball, nothing would happen. But if you hit it hard and it hit one of the other pool balls, that pool ball would move. So this is actually the material that Einstein was awarded the Nobel Prize for in 1921, not for relativity. So Einstein proved Planck was correct and verified that light was a particle. At least it is when it is absorbed and emitted, not when it's traveling. Okay, so I'm just going to put some math problems up here on the screen for you to look at. These are just some conversions for light. A rainbow numerically printed there on your outline could be useful. So if we have violet light that has this wavelength and that frequency, multiply them together on your calculator right now. This is what you're going to get. Now, if you take the wavelength and the frequency for green light and multiply them together, you get the same number, the speed of light. For yellow also. What if we're not talking about visible light? What if we're talking about radio waves? KMET was a radio station here in LA in the 1970s and 80s. Its wavelength times its frequency, and you get the same thing. All electromagnetic radiation travels at the speed of light. So, can you solve this? Pause if necessary. Go on to another one where we actually look for wavelength this time. I'm going through these kind of quickly, but you can pause as necessary. So all of those calculations were based on one photon. If we had 10 photons, all we have to do is multiply by 10. It's a mole of photons, all we have to do is multiply by Avogadro's number. Okay, folks, that is it for that part of the outline, and we will start up again next time. Hope you've enjoyed it. Everybody have yourself a good day.